Good day. We're going to start chapter 13. The topic is chemical equilibrium. In chemical equilibrium, the rates of forward and reverse reactions are equal. If we take a look at this first graph, we see that over the course of time, the rate of the forward reaction becomes aligned with the rate of the reverse reaction. So what becomes equal are the rates, the rate at which a reactant is turning into product and product is turning into reactant. Not the amounts, not the concentrations. So if we take a look here at a graph of concentration over the course of a reaction, we can see that we start out with a large amount of reactants, no products at all, and over the course of time, the amount of reactants should decrease in some fashion, and the amount of products should increase in some fashion, and the two rates become the same, not the concentrations, not the amounts. That period where the two level off is referred to as equilibrium. So at equilibrium concentrations, all the species remain constant, but not equal, yet only constant. Consider an equilibrium reaction that does not have a 1-to-1 molar mass ratio. So here we have a balanced equation with a 1 to 3 to 2 ratio. And on the reactant side, we have nitrogen and hydrogen. So what would I expect? That both of those reactants would start higher than 0, and that they would both decrease over time to some point at which they sort of stabilize. Is it reasonable to say that the hydrogen concentration is approximately 3 times larger than the nitrogen concentration? Sure, they are in a 3-to-1 ratio. The product, however, starts out at 0 and it ends somewhere between the ratios of 1 and 3. Its trend is to increase over time and eventually stabilize. So if you had a graphic like this and you were asked to determine where equilibrium begins or where you can designate equilibrium, it would be at the point where the concentration of reactants are stable and the concentration of products are stable. The three are not equal to each other, but they're no longer changing. They change relative to one another based on their concentrations. So how can we express this mathematically? Well, scientists have used the law of mass action to describe equilibrium concentrations in a reaction. This is the explanation for the law of mass action. Given the following reaction, where reactants A and B become products C and D, and the coefficients in front are just represented by these letters. This symbol here got changed, but it's just an arrow. The law of mass action states that the equilibrium constant, which is sometimes written with the subscript EQ, is equal to the concentrations of products raised to their coefficients divided by the concentration of reactants raised to their coefficients. So these letters got pushed down a little bit. This should be the coefficient, and then M and K. So K is called the equilibrium constant reaction, and the first thing we'll have to do for homework is to write the formula for K given a balanced equation. Write the expression for K. So given the balanced equation, notice that the products go in the numerator and their coefficient is the superscript. So this is raised to the second power, that the reactants are in the denominator and their coefficients, again, 2 and 1, are the superscripts. So this is the equilibrium expression for this reaction. Again, this symbol K sometimes has a little EQ and sometimes it does not. If you see the uppercase K in this context, you'll just consider it to be equilibrium constant, but sometimes we'll write an EQ there to distinguish it. Here's some sample problems. Let's give them a try. Products over reactants. You try the others. Now we're going to try some sample calculations where we actually plug in values to solve for the equilibrium constant quantitatively. Products over reactants. The superscript, remember, is the coefficient 2. Now I'll plug in the given values. Don't forget my units. Place that in my calculator. So I started with 3 significant figures. I want to end with 3 significant figures, and K actually is a unitless value, so I don't need to write any units for K. So this same equation can be given with 3 different sets of concentrations still at equilibrium. Because remember, equilibrium does not mean that concentration doesn't change, but it means that the rate of concentration doesn't change. So as reactants are turning into products, products are turning into reactants at the same rate. So if we go ahead and calculate these next 2 sets, I think what we'll see is all 3 sets have the same K. 3 different sets of concentrations at equilibrium give the same K. Each set is called an equilibrium position. So we can determine what the equilibrium constant would be at this position, or at this position of equilibrium concentrations, and we get the matching. So what we've actually seen an example of here is equilibrium position. And what that means is for a given reaction at a given temperature, the equilibrium constant, KEQ, will always stay the same, right? Several different sets of equilibrium concentrations can give the same KEQ. That's referred to as equilibrium position, or any valid set of equilibrium concentrations for a particular reaction. So here's a sample problem finding concentration using K, or relating those two things that we just learned about. So here's a given reaction, and they actually give us the equilibrium constant here at a given temperature. That means temperature is constant, it does not change. At equilibrium is found with the first concentration for water, then for diatomic hydrogen, and finally oxygen is the thing that we don't know that we have to find. So I think I would start by setting up our KEQ expression, which is always products over reactants. So we're going to write the concentration for this hydrogen, and remember its coefficient will become the superscript, and then oxygen, and its coefficient is 1, so I don't need to write a superscript of 1 there. And then for water, and finally, its coefficient is 2. Now, I can just start plugging things in, or I can rearrange for get rid of this fraction and just go ahead and multiply water on the left side, and then we'll have the remaining on the right side, and then we want to. Okay, so this is our newly arranged equation, and we can just go ahead and plug things in. I'm just going to move it over here so I have a little more space. My value for KEQ, my value for water, and remember that's squared. And also remember it really does have the units molarity because this is a concentration. Unlike KEQ, which does not have units, the constant here does not have units. So I plugged in everything matching my equation below, and then we'll just plug that into our calculator. I like to use parentheses so that my calculator knows to square before it multiplies, right? All right, so now I've got a bunch of zeros. Do I have any units? Is a good question. What was I solving for? I was trying to get the concentration of oxygen given KEQ. Of course, concentration does, those units would be molarity. And I've got this crazy number. Everything else has 2 sig figs, so I might want to get this down to 8.0. 1, 2, 3, 4. That's times 10 to the negative 4 molar. And that's what we have here at the bottom. Now, there are some sort of shortcuts to calculating K. Once you have K for a certain equation, if that equation somehow changes, you don't have to do all of the work again. So the equilibrium constant for the reverse reaction, for example, is simply the reciprocal. So if we take a reaction that was A plus B equals C plus D, and we flip that around so that it's now C plus D is A plus B, right? That's the reverse reaction. In this case, A and B would be in the numerator, right? And C and D would be in the denominator. So if you knew the KEQ value already, you could just simply take the reciprocal of it. You wouldn't have to plug everything in. So it's a nice little shortcut. Likewise, when the coefficients of an equation are multiplied by n, then the equilibrium constant can just simply be raised to the nth power. So when we're given an equation in which each of the coefficients can match, or we can make one overall coefficient for the whole equation that matches, then that can just become the power that KEQ is raised to. So it just gives us some other options, and here are some examples of how to do that. So we start out with an equation that's given, and the KEQ value for that specific equation. Now we're asked, what if the equation was to change in the following ways? How would we handle it? Well, which one of these looks easiest? My eyes are drawn to number 2 because it's simply the reciprocal of number 1. Everything about it is the same, right? We've got a 1 to 1 to 2 ratio. Here we've got a 2 to 1 to 1 ratio. All the same, reactants have become products and products have become reactants. So very simply, when the reaction is flipped around, then the reciprocal of KEQ is the new KEQ. So that would be 1 over 820, and remember that doesn't have any units. And so 1 over 820 is going to be 1.2 E negative 3. And you can go ahead and plug that into your calculator to check that, but just showing you a real quick shortcut that sometimes can be useful. Now, which other one would we like to try? Now, how about number 1? So let's compare the given equation, which remember it has hydrobromic acid in the numerator and the hydrogen and the bromine are in the denominator, and the KEQ value is 820. So if we take a look at this one as hydrobromic acid in the numerator, and it has hydrogen in the denominator raised to the 1/2 and bromine raised to the 1/2 as well. So what is the difference between these two? Well, the first one is really double the second one, right? The hydrobromic acid is 2, 1, 1. And here we have 1, 1/2, 1/2. So if we actually take this whole thing and we're really just raising the whole thing to the 1/2. So what that means is that we'll take the KEQ and raise it to the 1/2. So 820 to the 1/2, and that's going to give us this first value here. We already saw the second value there. So you can plug that into your calculator. Likewise, at the bottom, hydrogen and bromine, and the things in the bottom are the hydrobromic acid, right? And again, so there's two changes that have happened here. First of all, we flipped the equation, so that means that KEQ will become, though since the reaction was flipped, we'll start by taking the reciprocal of 820, and then we can simplify this entire fraction by raising it to the 1/2. So we'll raise 820 to the 1/2 as well, and we will get the third value for KEQ here. Sometimes we can find the equilibrium constant, but we'll have pressure data instead of concentration data. So from the ideal gas law, we know that pressure is proportional to concentration, right? Remember the ideal gas law, perv-nert? Okay, so another way of looking at perv-nert is that pressure is equal to, right, N over V. Well, that is concentration times RT. And R is the universal gas constant. T is constant because, as I told you, we're not going to be typically dealing with circumstances in which the temperature is changing throughout the course of the reaction. So that means that we can treat these almost as though they are the same. Kp is directly proportional to KEQ. Okay, and so that means the following expression is true. For the same type of reaction, right, we can put products with the superscript over reactants. But if we don't have concentration data, we can just do the exact same thing. KEQ is equal to K sub P, the equilibrium constant found determined by pressure. And we'll just be plugging in the pressure of this ammonia raised to the same coefficient, and the pressure of this nitrogen and the pressure of this hydrogen. So KEQ is essentially equal to KP with one exception. If the number of gas molecules of reactants doesn't equal the number of molecules of products, then there's an extra little step we have to do there. So Kp is only going to be equal to K. Remember, if R and T are constant and delta N doesn't change. Delta N refers to the difference. Remember, delta means difference, N is number of moles, and anytime we calculate a delta in chemistry, it's always products minus reactants, right? It's final minus initial. So we're going to be having to consider that, and let's do one of those now. So this slide actually has a couple of things that got reformatted improperly. So please just take a look so we can fix them. This should be degrees Celsius. See how it kind of got formatted weird? This is an arrow, not a box. Okay. And then a lot of my subscripts for these pressures got written like they weren't subscripts. So this is the pressure of chlorine gas, the pressure of nitrogen monoxide. Delta N here is a superscript. So it didn't get written as a superscript, and that's going to look confusing. So if you could please make those updates, that would be great. All right, so let's take a look at the equation we've been given here. 25 degrees Celsius, so we know the temperature is constant. The following pressures were observed. Okay, we've given all the pressures, so all we have to do is plug them in to find KEQ. Kp is going to be equal to the products. That's raised to their superscripts over the reactants, raised to their coefficients, excuse me. This does not have a coefficient. And then I can just go ahead and start plugging things in. So the 2. So the 2. And no superscript there. Okay. When I plug those into my calculator, 1920 is what I get. Let me think about that. Are there any units? Well, no. We're solving for the equilibrium constant, so there aren't any units. Even though we've used the pressure data, there still aren't any units. What about significant figures? All of the numbers had 2 sig figs, so I can round this off to 1900. That'll give me 2 sig figs. Those zeros are not significant with no decimal. So I have Kp. Now, K, the equilibrium constant, will be equal to Kp if the number of moles on the left and the right side of the reaction are the same. Are they? Well, we have 2 plus 1 on the left, so that's 3 total moles in a balanced equation, and then 2 on the right. So 3 on the left, 2 on the right, that is not the same. So delta N, we actually do have to consider at this time. Remember, delta is always final minus initial. So delta N is going to be 2 minus 3, which is -1. So since we know the Kp value, R and T are constants, we could easily plug those in. We will have to plug in a -1 for delta N in order to find what the actual KEQ value is. You see, if you write K like this without an EQ, it means equilibrium constant. Okay, if you don't see a subscript, then it's KEQ. KP that we do know are significant figures here, okay? And there are no units for that. KEQ, that's the thing we want to find. R is a universal gas constant, 0.08206 liter atmosphere Kelvin mole. You can look that up, and the College Board will provide you that on their standard sheet. Temperature, can we just plug that in Celsius? No, you know that we cannot. You know that we have to add 273 to change it to. Now, the superscript here is -1. Let's remember what that means. When something is raised to a negative number, that means it becomes the reciprocal, right? It's now in the denominator, right? Look like it was in the denominator. Okay, is simply going to be the 1900 multiplied by, okay. And again, this has no units, so, and I'm moving a little bit quickly to try to save my time here, but you go ahead and plug those values in and you're going to get 46,000.